Welcome to the fifth and final lesson in Chapter 5 of the Pearson Geometry video series. The last lesson concerned triangle inequalities in a single triangle. The sum of any two sides must be greater than the third, or an inequality arises and the triangle won't close. This lesson is concerned with the inequalities between two triangles. The hinge theorem says if two sides of a triangle are congruent to two sides of another triangle, but not the included angles, the side across from the larger angle is larger. So, looking at this diagram, we have two congruent sides and two angles that aren't the same. And so, since angle W is bigger than angle A, then side XY is going to be larger than side BC. And then we have the converse to the hinge theorem, and the converse to the hinge theorem says if two sides of one triangle are congruent to two sides of another, and the third side is not congruent, the larger third side will be across from the larger angle. So it works both ways. We have our two sides that are congruent. EF is greater than UV, which means that angle D must be larger than angle T. All right, let's see how we're going to use that. Example 1 demonstrates the hinge theorem as a physics application. It says the tension in the exercise band varies proportionally with the stretch distance. The tension T is described by the function T of x equals Kx, where K is a constant that depends on the elasticity of the band and x is the stretch distance. Which position shown in the figures has a greater tension in the band? So in this picture, his arm and his height stay the same. Arm is still the same length, height is still the same. The difference is that he's lifted his arms up, changing this angle right here. Also lengthening the distance from his feet to his hands where the band is. So which do you think has the greater tension, LK or MK? All right, so we can see that as this angle changed, this side got longer. Suppose the distance the tension band is stretched does not change. In other words, this length of his arms and this length of the band stays the same, because instead he's going to bend his knees. All right, so if that's the way that it's moving, then let's go ahead and change that. We will change the distance between his shoulders and his feet, and then the arms are going to stay the same. And so the triangle is now going to look something like this. So in this case, what changed? So now, since this is shorter, this angle is the same. So it's this angle that's gotten smaller. Okay, well, let's take a look at example 2. Example 2 is kind of complicated. It is a very good hinge problem, though. Vertical angles don't apply because we have two sides that are the same, but we do not have two sides here that are the same. So that being the case, we can look at this and figure out a range that x must be. We can't figure out what the exact measurement would be. So if we look at these two sides, since 18 is greater than 14, then this angle, represented by 2x minus 4, must be greater than this angle, which is 36. Okay, looking over on this one, we still have two sides that are the same. This is the included angle, just like these are the two sides that are congruent, and this is the included angle, and these two sides are congruent, and this is the included angle. So, that being the case, the third side, 21, is greater than 18. So, if 21 is greater than 18, then that means that 60 must be greater than 2x minus 4. What these two inequalities tell us is that the angle measure, represented by 2x minus 4, is going to fall between 36 and 60. Okay, so if we write that out algebraically, it looks like this. 36 is less than 2x minus 4, which is less than 60. And let's go ahead and solve that. We can start by adding 4 to both sides. So if we add 4 to the left, we're going to get 40. If we add 4 to the middle, we're left with 2x. If we add 4 to the right, we get 64. Now we can divide everything by 2. The left becomes 20, the middle becomes x, and the right becomes 32. So it appears that the angle, or the value for x, is going to fall between 20 and 32. Example 3 is similar. Looking at this one, again, we can't use the vertical angles. This is not a straight line through here, and these two sides are not congruent. So, since 10 is less than 12, then 4x minus 18 is going to be less than 54. So we can add 18 to both sides, and we're going to get 4x is less than 72. Divide both sides by 4. And x must be less than 18 degrees, or 18. Okay, flip this over. Let's take a look at example 4. In example 4, still same problem. We've got two sides and two sides that are congruent. This is the included angle here, represented by 3x plus 5. This is the included angle here, represented by 32. So, since 21 is greater than 16, we can say 3x plus 5 is greater than 32. If we solve this, we're going to subtract 5 from both sides. So 3x is greater than 27, and divide both sides by 3. So x is greater than 9. All right, example 5. This one involves a map. So looking at this, we could draw the route each plane took, or we could just use a straight edge and draw right on the diagram. Let's do that. Okay, so we've got, this is the shortest distance to the airport for plane B, and whoops, let's try that again. And this is the shortest distance to the airport for plane A. All right, so it was going straight, or let's start with plane A. Okay, so plane A was going straight this way and then veered. So to figure this angle out right here, we can take 180 and subtract 15. And when we do that, we're going to get 165. That means that this inside angle is 165 degrees. Okay, doing the same thing over here to figure this one out. If this is 20, and we're actually looking at a linear pair right here, then we can take 180 degrees minus 20, which gives us 160 degrees, which means this inside angle right here is 160 degrees. Since this one is 165 and this one is 160, then this distance is going to be longer than this distance. So that means that plane B is closer to the airport. All right, example 6 is very similar. So if we figure out what this angle is right here, then we can determine which boat is closer to, or which kayak is closer to the dock right here. So we have 180 minus 50, which is going to give us 130 degrees. Here we have 180 minus 45, which is going to give us 135 degrees. So kayak B has a larger angle on the inside, which means it has a farther distance to go, and then kayak A, so kayak A is going to be closer to the dock. Okay, finally, last example. And this one is a blast from the past. So reaching back, we're going to find the orthocenter of a triangle. Now, this one, I started out by graphing the points. They didn't tell me what points they were, so I went ahead and named them because I think it's easier to work with the points when you know what their name is. It's easier to work with anyone when you know what their name is. So I'm looking at this triangle, and it looks like it might be a right triangle. And right triangles have some properties that make the orthocenter really easy to find. So let's figure out what our slopes are here. Looking at AB, the slope of AB is going to be up 1, 2, 3, 4, and over 10. So 4 over 10, which reduces to 2 over 5. Now let's figure out the slope of CB. The slope of CB is going to be down 1, 2, 3, 4, 5, and over 2. So negative 5 over 2. What we have right here is perpendicular slopes. So that means that what we have here is a right triangle. If we look at this triangle, so that this is the base, from vertex C, the altitude straight down is going to be this line right here. If we turn it around this way, so that BC is the base, the altitude from point A is going to be straight down right here. So it looks like this is where they intersect, and that is going to be where our orthocenter is. So our orthocenter is going to be at 10, 4, which is point B. Well, now that was easy. Every now and again it does work out a little bit easier for us. All right, so that's it for Lesson 5 and Chapter 5. See you later.